Hello everyone, welcome to the class ECE317 Digital Signal Processing. Last time we introduced the way to solve difference equation with initial condition, right? Today let's keep working on the same topic. We will discuss more examples. Okay, this is a ECE 317. This is a Wednesday's class. Which week? 5th week. Okay. I still use the same example, right? Same example. That is here I have notes of last time in my hand. Let me copy it. It's the system certified equation. This is the equation y of n plus 1/6 of times 1/6 times y of n minus 1 and minus y of n minus 2 minus 1/6 times y of n minus 2 equal to x of n minus 1/4 x of n minus 1. We call this equation as a 1, first equation. And the input signal, it is x of n equal to 1/4 to the power n times u of n. Okay. And we want to find the output. Find the output. Actually, we have an initial condition. What is the initial condition? Initial condition y of 0 equal to y of -1 equal to 1, right? And our result is step 1. Find a particular solution. Actually, I say a particular solution, one of the particular solution. You can have more than one particular solution, depending on your method. We use a Fourier transform, we can have one. And later you should know, if you use Z transform, you may have some different kind of particular solutions. So we find one particular solution. We can work like this. We have the frequency response, right, equal to, you check the system, you know this is 1 minus 1/4 e to the negative j omega, right? These two coming from the right side of the equation, system equation, right? And the denominator coming from the left side, the coefficients of those outputs. So this is 1 plus 1/6 e to the negative j omega and minus 1/6 e to the negative j 2 omega. Okay. This is a transfer function. Frequency response. And then we have the output, which were equal to h times x. And x in time domain is this one. So in frequency domain, x will be 1/1 minus 1/4 e to the negative j omega. Right? So the result is h times x. This is h. This is x. So times these two together, you see they cancel, right? The numerator and this one, they cancel. So equal to 1/1 plus 1/6 e to the negative j omega minus 1/6 e to the negative j 2 omega. And then by partial fraction, we can have, okay, I just copied the result of last time. It is this is a 0.6 over 1 plus 1/2 e to the negative j omega, and b is a 0.4 over 1 minus 1/3 e to the negative j omega. Alright, then we have the result in time domain, y of n by inverse dtft, right? dtft, discrete time Fourier transform, the inverse. Then we have this one is a 0.6. Then, okay, here I needed minus negative 1/2 to the n, u of n, and plus 0.4. This one is 1/3 to the n, u of n. Okay, this is a particular solution. Then the second step, step 2, we need to find the homogeneous solution. Homogeneous solution. This one, actually, depending on homogeneous solution, just depending on the original equation, you just remove this part. You let x equal to 0. Right? You can say let x equal to 0. Homogeneous equation, consider the equation is this: y of n minus plus 1/6 y of n minus 1 minus 1/6 y of n minus 2 equal to 0. This is equation 2, the homogeneous equation. Okay, so to solve this one, you just suppose y of n equal to lambda to some n. Then you can have lambda to the n plus 1/6. This is a lambda of n minus 1, right? Y is lambda to n. The y n minus 1, you just replace n by n minus 1. And similarly, this is 1/6 lambda n minus 2 equal to 0. Okay, then we can solve. The result is lambda equal to, I don't go over the process, I just give the result here. You can check the notes of last time, you can know the result. It will be lambda equal to 1/3 or negative 1/2. Actually here, you can solve these to get it. You can also consider they are the coefficient in previous step. In previous step, you can see here h is the y is this one, right? Y is this one. Then we have 1/3 and the negative 1/2 as a coefficient here. You consider this is 1 minus a e to the negative j omega. This one, a equal to negative 1/2 or 1/3. Right? These two terms, their things look like this. Okay, here you see you have a negative 1/2, you have 1/3. Okay, see? Just these two numbers. So for this part, you can solve it, but you can also find this lambda directly. Just use these two numbers from the first step. Use this first step by DTFT method. Then you have these two numbers. Okay, now you know here lambda must be these two numbers. If the system has higher order, like here I have the system y divided by 1 divided by 2, so the order is 2. It's order 2. Second order system, right? Order 2. Order 2 on y. Order 2 on y. Then here we have two this kind of coefficients, and this one is also order 2, right? This is order 2. only y, no x, right? So order 2 on y, order 2, and 2 solutions of lambda. So this order 2, you have 2 solutions. If this is order n, then here you will have n solutions of lambda. Alright. In this example, we only have 2. If you consider some high order system, then here you maybe have more lambda, depending on the order. Okay. Then we know y of n can equal to 1/3 to the n, or negative 1/2 to the n. It can be either one. And as the system is linear, so you just add them together, and each one times a coefficient alpha 1, alpha 2, they will be the solution of 2. And I gave a name, homogeneous solution, YH, homogeneous solution. So this is a homogeneous solution. Alright. Where alpha 1, alpha 2, any constant. So far we cannot determine the value of alpha 1, alpha 2. We need to determine them based on the initial condition. So now we can say we have all the possible solution of the system, of the homogeneous system. So now we already obtained all of the homogeneous solutions of the system. Yeah, all of the homogeneous. We want to find homogeneous solution. We found not just one. We have infinite. Right? All the possible. Yeah, all of the homogeneous solutions. Like in this one, you can imagine it's a kind of a two-dimensional space, right? You have a lot. You have 2 parameters, could be any number. Then step 3, we need to find the final solution of equation 1, with the given initial condition. Initial condition. Given initial condition. We have given initial conditions here. We have y of 0, y of -1 equal to 1. So actually here, the thing is, I have 2 initial conditions here, right? Initial value, 2 initial values. So in generally, how many initial values are necessary and enough to work? So here, firstly, I mentioned something here. The original equation 1 can be written as this. The original equation is here, right? In this one. Now I move these 2 terms to this side. Then I have, can I see both? Okay. y of n equal to this side we already have x term, right? X minus 1/4 x of n minus 1. They are already in the right side. And now I move two more terms from left to right. So I need minus 1/6 y of n minus 1 and plus 1/6 y of n minus 2. And we have this. Okay, when n equal to 1, that is y of 1 equal to x of 1 plus minus 1/4 x of n minus 1, and n minus 1 is 0, right? 1 minus 1, and minus 1/6 y of 1 minus 1, and plus 1/6 y of 1 minus 2, right? Apply n equal to 1 here. And this is x of 1 minus 1/4 x of 0 minus 1/6 y of 0 plus 1/6 y of negative 1. So you see, if you want to determine y of 1, you need y of 0 and y of negative 1. So okay, we have to know these two values. Right, we have to know these two values to determine y of 1. Alright, yeah, we have to know these two. If we do not have these two values, we cannot determine y of 1. Okay, so this is the initial value. They are the initial value. And then you look at the original equation here. I put these two together. This is the original one. Now, when n is 1, I get this. So by this way, we can determine y of 1 if these two values are given. After I get y of 1, I can get y of 2. Y of 2 will equal to some value from x, and okay, y of 2, here n is 2. Here will be y of 2 minus 1, y of 1. And here is y of n minus 2, 2 minus 2 is 0, y of 0. So y of 2 will depending on y of 1 and y of 0. Y of 1 is calculated here, and y of 0 is given. So we can have y of 2. And then you can repeat this process. Every time you want to find y of n, the value is coming from y of n minus 1 and y of n minus 2. So these two values are two early values. Okay, this is time n. Like now is for example, now is suppose like now is 3 o'clock. Y of 3, or depending on of the value of y at y of 2 and y of 1. Right, 2 n is 2. Now here is 1 2 and here n is 3. Here n minus 1 is 2 and minus 2 is 1. Some early values. So output of y depending on some value from input and some early values. So you by this method, by this formula, this equation, you can find the new output step by step. But you need to start from initial value, just like this. If you do not have these two values, now you cannot start your calculation, right? Okay, so these are the initial value. Okay, so this is in this example. In this example, we need two initial value. 2 initial value. And in general, we need for order n system, okay, how to say, I write here. This is the order 2 in Y, right? The system is order 2 in Y. Then we need 2 initial value. 2 initial values. And then generally for system with order n in the Y, we need n initial values. For example, to determine the output, of the system, like y of n plus is 1, 2, y of n minus 1 plus 3 y of n minus 2 plus 4 y of n minus 3 plus 5 y of n minus 4 equal to x of n. Like this one, we want to determine the output. We need how many initial values? How many? You check the order. Here's n minus 4. This is order 4. Order 4 on y. Right. Original y and shift by 1, 2, 3, 4. Okay. So we need 4 initial values. That is a y of 0, y of 1, negative 1, y of negative 2, y of negative 3, 1, 2, 3, 4. Yeah, we need 4 initial values. Alright, okay, so this is about the initial value. And in this example, in our example, this one, right, we're trying to find the equation in this one. In this example, the order is 2, so we need 2 initial conditions. And actually, we already have these 2 initial conditions, right? So based on these 2 initial condition, initial values, we can find the final answer. And also, for the homogeneous solution, you see, we have lambda, we have 2 solutions on lambda, so homogeneous solution looks like this. We have 2 unknown constant, or we say 2 free constant, right? Free coefficients. They could be any value. They are free, right? We have 2 free. And if the system has order n on y, order n, then we have n solutions of lambda. Then we have n free coefficients, alpha 1, alpha 2 until alpha n. Then we need, you want solve to find those r, you need n initial condition, right? So this is another way. You start from the system equation, the equation here, you know you need n initial values if the order is n. You can also consider the homogeneous solution. You have n free coefficients. To determine these n free coefficients, you need n initial conditions, initial values. Okay. All right, let's go back to our problem. This is step 1. Find the particular solution. Okay, step 2. Step 2, find the homogeneous solution. Now we go to step 3. We need to find we need to determine those unknown values based on the initial condition. Okay, so we have these. We have y, I say it like this. We have yr of n equal to y particular solution plus y h of n. I say r, that means all possible solution of the given system, the original system, right, of y. And this one, actually this yh, they are all possible solution of the homogeneous solution equation, the homogeneous equation. That is equation 2. Equation 2. You just remove all the terms with x terms, right? Remove them, let them equal to 0. Right. So we already have this one. Then by the initial condition, we have y. Okay, I write this yr of 0 equal to what is the initial condition? Step 2. Step 1. This is 1. Okay, I give this as the initial condition. Both are 1. 1 yr negative 1, it is also 1. We have this. Alright, then we can have y particular 0 plus y homogeneous 0 equal to 1. Y particular at negative 1 plus y homogeneous of 0 equal to 1. We already solved this, right, last time. So here I just copy the result. Okay, we have this. We have alpha 1 times negative half 0 plus alpha 2 1/3 0. This is 0, and alpha 1 negative 1/2 to the negative 1 plus alpha 2 1/3 to the negative 1 equal to 1. Yeah, you can check the notes of last time to find this part. We already have this. And then we have alpha 1 equal to which one? Alpha 1 is negative 1/5 and alpha 2 is positive 1/5. So we have this. Alright. We have alpha. Then we can determine what is the final answer. Here for this yr, all possible solutions, because in yh we have two free coefficients, alpha 1 and alpha 2 could be any value, so give us all possible solutions. We have a lot of solutions. And now by this initial condition we have two particular value for those free coefficients in yh. So we have the solution of 1 satisfies the which satisfies the initial condition, the given initial condition, is y of n. Okay, now I remove all. This is not all solutions, this is just one solution, equal to y particular solution plus that yh of n, the homogeneous solution, but now the alpha is given, and I copy yh, yp, okay, yp is here, yp is 0.6 negative 1/2 to the n, and u of n plus 0.4 1/3 n u of n, and plus YH. I need alpha 1 times alpha 1 times alpha 1 is this. Oh, this is minus 1/5 alpha 1. Alpha 1 times the here. Alpha 1 times 1/3 to the n. Right? So here's alpha 1 times 1/3 to the n. And alpha 2, oh, wait. This alpha 1, alpha 2 is, do I use the same alpha 1, alpha 2 than last time? So I have negative 1. Sorry, when I copy, I make something confused. Last time alpha 1 is a coefficient of negative 1/2. So this time the solution will be different. We will reverse the order. Okay. So alpha 1 is a coefficient, you see, alpha 1 is coefficient of 1/3, so this is alpha 1. And alpha 2 is the coefficient of negative 1/2. Yeah, last time I reversed the order. Yeah. So, okay, should be this one. Then this is alpha 2, this is alpha 1. Okay, now it's good. And then our answer will be alpha 1 is related with 1/3 is positive, and alpha 2, now this is minus 1/5 related with negative 1/2 to the n. Okay, so we have the final answer is this one. It is one. Alright, we are done. Now we look at, we want to know here alpha can change, right? Alpha, for these two alphas, we know the solution with this given initial condition. If initial conditions change, that means if these two numbers are changed, what will happen? So let's have a look. We can do this use MATLAB. Okay, the MATLAB. All right. Yeah, we have this solution of the whole system with the given initial condition, and we can have a graph to see how do they looks like. Right? We can have the graph of the particular solution, the homogeneous solution, and the whole solution with the given initial condition. And actually, by computer, we can do more. We can select the different initial condition, and we can see what will happen, what will be the final answer. Here we just get one, right? This is for one initial condition. For the more initial condition, you need to do more calculations, but we can use computer to do this. All right. Okay, so okay, we want to display y particular solution, so we want y particular solution, we want y homogeneous solution, and of course we need a time interval n, like we suppose run from -3 to whatever, like 8. Yeah, if it's not enough, we can change it. And the y particular solution, okay, is here. No, this is not particular solution, this is the whole thing, right? Alright, the first two terms are particular solution, the last two terms are the homogeneous solution. So particular solution is 0.6 times -1/2 to the power n. Now n is a vector, so I need to put a dot here. Plus 0.4 times 1/3 to the power n. Okay, this is a y particular, and we can have a look of these. So we can have a figure, the first figure, figure 1, stem n and yp. Okay, this is the first one. The second one, we want homogeneous one. Homogeneous one, okay, y edge is actually that will be alpha 1. I use a1 times, that is 1/3, 1/3. Okay, 1/3. I put negative in front. Negative 1/2. I use the same order. Let me use the same order. Right? Yp is a negative 1/2 in front. So here I also use negative 1 in front. And to the power n. Oh, I lost the u of n. Sorry. Here I need a u of n. U of n, the unit step, which is just I use a logic operation, n larger than equal to 0. Then yeah, this is a, so this part from n to 0, this part is a logic operation, right? So for all the negative n, the answer is no, it is fail, it's 0. And when n is larger than or equal to 0, the answer is 1. So this is unit step. And here y of n, I need times unit step. Actually, both terms I need u of n, so I can put the u of n together. Times, dot times u of n. Alright, this is yp. And y edge, yeah, this time just the power, we don't need that one. And plus a2 times 1/3. Oh, which one is a1, which a2? I'm confused again. Anyway, I just use this in the code. Alright. Now how to determine a1 and a2? I can just copy this here, and actually we can use different initial value, right? So I can use y initial, y of negative 1. I just use this for the initial value, y of negative 1, right? I use this is some any value. First of all is 1, as we did in the example, and y of 0, yz, okay, y of 0, it is also 1. And then we have a1 and a2. What is a1 and a2? Yeah, we saw a1 and a2 by the initial condition, right? Now we use 1 and 1, and we can change these two values. Then we have, this is 1, this is a, oh sorry, I have to correct, this is negative 1, negative 1. Yeah, typo here, should be negative 1 here, negative 1. When it's a negative 1, this is another initial value. Then we plug in y particular and y edge, we have these two. So if here is some let's say this is yz, this is some y negative 1, then here will be still y negative 1, right? And here will be 0, y0, or minus y particular is 1. Y particular of 0 is 1. This is 1. This is 1. Y particular solution, which is y particular solution. Yeah, I see. This is y particular solution, right? When n is 0, so it's 0.6 times 1 plus 0.4 times 1, so it's 0.6 plus 0.4. It is just 1. Alright, so this is 1. Well, particular of 0 is 1. Right, we have this. So this value, it is y, the initial value of z minus 1. It is this value. So when we pick different initial value, we can just use these two to be here, to the value here, then we can solve this equation to determine these two alphas, or 1/3 according to alpha 1. Sorry, the notation. Last time I used different notation. This time I use this, and in my code I go back. Okay, I use this one. Okay, looks better. Easy to enter. Sorry, here still A2. Yeah, sometimes you choose the right notation can make things simple. Here I make a little bit confused. All right, I use this one the same way as the notes in today. Okay. Then we need A1 and A2. We need to solve this equation, right? So this equation, the coefficient matrix, I need the matrix A equal to the coefficient is, you see the coefficient here, alpha 1, the first coefficient is 1. This is also 1. This is 3. This is -2. So we have A is A1's coefficient is 1 in first equation. And A2 has coefficient is also 1. In second equation, A1 has 3 as the coefficient, and A2 is -2 as a coefficient. So this is A. This is A, right? Then we need. I see the answer is some A. I use B as the answer. That will be the inverse of this matrix A times the coefficient now is first equation, the first element, it is y of 0 minus 1, and the second one is y of -1. Oh, it's a column vector. Alright, so we have this one, we have B. The A1 is it is just the first element of B, and A2 is the second element of B. Okay, I get A1 and then B, then I plug in, I have YH. Alright, now I can plot as a figure 2, plot, and not plot, a stem, which one? Stem N and YH. Okay, so this is the homogeneous solution. We can see what is homogeneous solution. And finally, I need to add them together. So that is a figure 3. Figure 3, stem N, and okay, here just YP plus YH. I can just use this, or maybe I define the YR, which is YP plus Y homogeneous, particular plus homogeneous. And here is just YR. Not really YR. Actually, this is the YR with the given. The 1 in the YR satisfy the given initial condition. Alright, let's run it. This is we need to put the file in 317 folder and save it. F5, save and run. F5. Okay. F5. This is this folder. We need to save this is a lecture, the 5th week, Wednesday's class. Oh, I already have one. Actually, this is a one in the last semester. Should be similar. Maybe some notation is not exact same. Let me cover it. Replace it. Yes. Okay, run it. Alright, we have 3 figures. Figure 1. This is a particular solution. It's given by the Fourier transform, and the result contains U of n. So all the non-zero values, they are in the positive side for positive n, right? For positive n, here n equal 0, 2, 4, 6, 8. We have some values. So this is a y particular solution. And the figure 2, this is homogeneous solution. Homogeneous solution, it go over from negative to positive infinite. All of them, they might be non-zero values. You can see we have a lot of non-zero values, right? All of them. No u of n, right? We do not have u of n in the term, so we have these. Then the final answer is summation of these two. Okay, this is combined of, can I put them or? And you can see, yeah, almost all of them, right? Yeah, combined of these three, we have the final answer. And the initial condition should be 1 and 1, right? Am I good? There's something wrong. Oh, here I missed the dot, the power. All right. Okay. Let me run again. F5. All right. Now it's good. This is a particular solution. Actually, the same way last time. And this is the homogeneous solution. And you can see we already have the. Oh, this is not the initial condition, but we have 1 and 0 here. This is a particular solution. When I add the particular solution, this is homogeneous solution. Figure 2 is homogeneous solution. When I add them together in figure 3, this is the final answer. This is a solution with a given condition, given initial condition when time n equal to 0 and 1. The values are 1 and 1. Okay, this is given initial condition. And here we can make some changes if we choose different initial value. For example, here I use 3. Okay. Now y of negative 1 is 3. What will happen? F5. Okay. The particular solution is same. Homogeneous solution where there will be something different. And here's the final answer. Initial value at 0 is 1, at n equal to this negative 1, this should be 3, right? This is 5 here, so this is 3. The value here is 3. Which one I can see the values. We should have a way to see the values, right? Anyway, I forgot that method. You should know that, right? You can try this code in your computer, and then you can see here should be 3. Yeah, it's a 3, right? It's a 5. Here should be 3. So initial condition. If we change different initial condition, like I use here's a negative 4, for example. What I have? F5. Okay. Particular solution is same, homogeneous solution is this one, and when we combine them together, the initial value will be negative 3 and negative 4 and positive 3, right? This will be negative 4 and that will be negative 3. This is the final answer. Yeah. Okay. Yeah, that's all for today. See you next time. Bye bye.